Our next speaker is Andrea Pelissetto. Please, Andrea.
Okay, thank you very much. It's a pleasure to be here for this Sergio's occasion. And I just want to remind a few things about our long-standing collaboration, friendship, and everything, which intertwined our personal and physics life. I met him, I think, 37 years ago during the nights, because at the time the students were not allowed to use the computer center during the day. So we were meeting at night. I was writing the thesis, the master thesis, and he was just, I don't know, probably checking programs. I have no idea what he was doing. But usually at 9:30, we're just meeting at the computer center, say a few words, then working. And that was the first time we met. And he was just wondering what I was using, what I was doing with his advisor, previous advisor, with Pietro. And then we began working on gravity things, numerical things. I remember I had no idea what a computer was at the time. And I was given a program by Massimo Campostrini. Then I had a Cray assembly language program by Guido Martinelli, and that was all. I never had an experience on anything, never done anything on any computer. I just had this Fortran code, Cray assembly language code, and that was it. Yes, Guido Martinelli provided a Cray assembly language, because at the time, the basic routines of the Monte Carlo had to be really written in assembly. Otherwise, on the Cray, they were not going very fast. You were losing 30% of the... Yeah. We were really moving things in the registers. It was really hard work. So I had this experience, and then a lot followed. And here I have, I hope it works. That's it. It should. Oh, I'm pressing this one. Okay, it moved. Okay, so it's 36 years ago, the collaboration, but as I said, we met 37 years ago. And I just looked on the ISI database to see how many papers I had done with Sergio, and I realized I have a lot of them. There are 74 of them that we have written in a span of, I think, 25 years, more or less. And this is our first paper, the paper we began with, which was published in 87, so a long time ago, 35 years ago. And that was the first of a series of papers that we also done with Pietro and on this subject. And then we moved to many other different things. And I remember in the same year, in 87, Alan was in Pisa for his usual summer period. Every summer he was there, I remember. And then I began to be involved in what was called the FACF algorithm, the Baer-Förster, Aragão de Carvalho, Caracciolo-Fröhlich, if I remember correctly, the meaning of those letters. And then I began to move on the soul things, and then we started studying sigma models and many other different subjects, which, okay, it was a very fruitful collaboration. I'm very glad of having been able to work with Sergio, because he really gave me some very good introduction to physics. When I was very young, no idea what to do, and Sergio and Pietro were really two people that provided me the guidance which a young guy needs to go into physics. So I'm really happy to be here for this occasion. And the talk is in some sense in the line of the things that Sergio would have liked, because it's some kind of work in which you try to understand things deeply, and not just to do some work, but you really want to understand how things go, and you will see. So with the talk, I hope it moves. Why it doesn't? I'm pressing, moving one side to the other. It does.
Sto qui, guarda, mi metto qui.
I have no idea. Maybe you're, I don't know. So the subject of this talk is related to some interest which we have nowadays in emergent gauge theories. And emerging gauge symmetry, the concept of emerging gauge symmetry is one of the most interesting new concepts that we have now. And the idea is to take models in which there is no gauge symmetry at all. They just have global invariances. And then you have some kind of quantum system. And then the basic tenet, the basic idea of this approach is that at the critical point, the relevant excitations are gauge invariant. So there are some gauge fields that emerge. This is why there is an emergent gauge symmetry that only emerge at the critical point, and they provide the relevant order parameter for the transition. So it's a really new paradigm which has appeared in the condensed matter community due to Sachdef and Sandhill and a few other guys, which provides a new way of looking at quantum transitions. In cases in which under the usual Landau paradigm, you would expect a first order transition because the symmetry, the global symmetry of the phases is completely different. And in this case, according to the Landau paradigm, you would have a first order transition. But in this new approach, you may not necessarily have, but you may have a second order transition. So there is a nice example of this. Here. There is no way to move on using the computer? Okay, I think I will use this method, which is much easier and faster. So the simplest example is a model which is not realistic, but it's provided by Sachdef. And the model is the following one. It's a very simple spin 1/2 antiferromagnet on the lattice, in which you have the standard Heisenberg interaction. And in this model, you have two types of interactions: the interactions on the bold, on the thick lines, and the interactions on the dashed lines. And in principle, they are different. The model is antiferromagnetic. As you see, there is no minus sign. And so if all couplings are different, are the same, you get the usual antiferromagnetic Heisenberg model, which has the usual nail or the parameter, and has gapless excitations, which are the usual spin waves. So if all couplings are equal, there is nothing going on here, and the model is trivial. Instead, imagine that you don't have, that the couplings on the dashed lines are exactly zero. So you only have the couplings between the thick lines. Yeah. Okay. So you just have the coupling between the thick lines. And in this case, of course, it's a trivial quantum mechanics problem that the ground state is just obtained by coupling the two spins, and you get singlets. So the spins are just in configurations of a total spin equals 0, and the triplets are the excitations. Then, of course, you can just interpolate between the two models, just switching on the coupling on the dashed lines, and you get something which interpolates between a ground state made of singlets to a ground state in which the system is antiferromagnetically ordered. And of course, there is a transition in between. And the theory which has to be developed is the theory for this transition. And the main problem here is the order parameter. What is the order parameter of this transition? Because apparently the two phases are completely different. In one case, you have an antiferromagnetic phase, and in the other case, you have just a paramagnetic phase with simple singlet states, which are obtained by coupling neighboring spins. So this is the idea. And okay. And the solution proposed by Sachdef and others is that of introducing what's called fractionalization. Fractionalization means the following. The spin S, you can, of course, represent in terms of a spinner, just by using this very simple formula, Z bar sigma Z. This is just a change of variables. You're not adding anything. But of course, if you represented the spin in terms of the spin, which is the field Z, of course, you're adding degrees of freedom, and you are introducing some kind of gauge invariance. Of course, if you change Z by a phase, the spin is identical. At this level, the gauge symmetry is introduced as a kinematical parameter. It has no meaning whatsoever. It's just a way of cutting out the degrees of freedom that we have introduced by changing variables. But then the idea is that of introducing beside the gauge symmetry also gauge field. So the idea is that we introduce also gauge field, that this is not present in the original theory. And why we do that? We do that because if we introduce a gauge field, the gauge field provides an order parameter for the other phase, for the paramagnetic phase in which you have singlets. Because otherwise, S or Z equivalently is only an order parameter for the anti-ferromagnetic phase. So by adding a gauge field to the theory and obtaining gauge invariant model, you obtain a system in which you have an order parameter for both phases. For the paramagnetic phase, in which you just have this singlet states, and for the anti-ferromagnetic phase, in which the order parameter is the usual Néel order parameter. So this is the idea. And then if you go from quantum model to the classical model in 2+1 model, you just get the abelian-Higgs model. So you get a gauge theory with a simple scalar field, a complex scalar field, which is the... So let's now go to the abelian-Higgs model, which is now a completely classical object. And it's standard for people working in lattice gauge theories. This is just matter interaction. So you have a field Z, which is just an unit complex vector, which is ferromagnetically coupled together with a gauge field lambda. Lambda, which is a phase which makes the matter action gauge invariant. And then you have to provide also an action for the gauge field. And there are two choices. We are in an abelian model. So you can get, you can use the usual Wilson action, exactly as we do in the non-abelian case. But in this case, you can also use the non-compact action, as was advocated in the high energy physics community, for instance, by John Coggott. And the gauge non-compact action has some problems. For instance, you cannot use periodic boundary conditions, because if you use that, you have Polyakov loops which are not bounded. And so, if, for instance, if you do the simulation, of course, if you do the simulation in the non-compact model, you see that, of course, the fields make a random walk. They are not bounded. They just move around in configuration space. But if you use periodic boundary conditions, also the Polyakov loops are not bounded and make a random walk in configuration space, which is somewhat dangerous because the Polyakov loops are gauge invariant. So when you use the gauge non-compact action, you never use periodic boundary condition, but anti-periodic boundary condition, because anti-periodic boundary condition kill this Polyakov loops and eliminate this problem of non-bounded gauge invariant excitations that are present in the model. How do we how do we interpret the behavior of this model in the field theory framework? So there are essentially two approaches, and both work in the appropriate regime. The first possibility is the so-called Landau-Ginzburg-Wilson approach, in which one assumes, as essentially an assumption, that the critical dynamics is only controlled by the gauge invariant degrees of freedom that are present in the model. So the known gauge invariant degrees of freedom are irrelevant. And in this view, the gauge fields, which are not gauge invariants, of course, don't play any role. So essentially, the idea is that you use gauge invariance to define your order parameter, because the order parameter should be gauge invariant. So gauge invariance is important in the sense that it defines what the order parameter is. But once you have the order parameter, you simply write the most general scalar theory in terms of your order parameter that respects all the global symmetries that you have in the model. And then the claim is that the critical behavior is controlled by this scalar theory in which there are no gauge fields. So it becomes a standard Wilson theory, which can be studied using the standard approaches in statistical field theory. And indeed, this was the approach which was taken by Pisarski and Wilczek when they tried to describe the the finite temperature transition in QCD. Essentially, they did the same. They just used the order parameter, which is a gauge invariant quantity. They wrote a theory for the gauge invariant order parameter, and they assumed that that non-gauge theory, that scalar theory, was providing the correct description of the phase transition. This is one possibility. The second possibility is, of course, that there is a counterpart of the lattice gauge abelian model, which is the continuum field theory. And you may assume that that continuum field theory has something to do with the critical behavior. The second possibility is that the critical behavior is not controlled by the same theory as in the previous approach, in which we are integrating out the gauge fields, but the gauge theory which is naturally associated with the abelian Higgs model. So by the gauge theory in which you have scalar fields and gauge fields minimally coupled, exactly as you do in high energy physics. And of course, you can apply the standard Wilson-Fisher approach also here. There is nothing that you cannot do here. And you can look for fixed points for this global theory. And the interesting thing would be to find charge fixed points. Charge fixed points are those fixed points which are obtained in the normalization group approach with non-vanishing values of the gauge coupling. So you have a fixed point in which the gauge coupling is not vanishing. So this means that the gauge coupling is relevant at the transition. And they obtain new fixed point, new field theories. And those field theories cannot be obtained in the Landau-Ginzburg-Wilson approach. So we have two different approaches. They have different predictions. The problem is what is happening in the real model. So if we do the simulations in the lattice model, do we observe Landau-Ginzburg-Wilson behavior or field theory behavior with gauge fields? This is essentially the approach. Of course, if you do field theory, you can do the 4 minus epsilon expansion, and this has been done. So let's see the two different predictions. In the Landau-Ginzburg-Wilson approach, essentially, you can have second-order phase transitions only when the number of flavored, the number of components of the scalar field is 2. This is the only possibility in the O3 universality class. But in all the other cases, only first-order transitions are possible because there are no fixed points. So if you do the analysis of the fixed points of the scalar model, you find fixed points only when the number of flavors is 2. On the other hand, if you use the abelian Higgs field theory, you find that some charge fixed point exists. You can do this 4 minus epsilon expansion to get this expansion that tells you that fixed points should exist when n is larger than some critical value, which is predicted by the epsilon expansion to be very large. We don't know how large it is because this is this function. As you can see, the numbers are huge. So it's very difficult to get something reasonable out of that. It has been done, but requires some additional assumptions. But in any case, it indicates that if n is large enough, something happens and a charge fixed point exists. Oh, this is just calculation. You do the calculation at one loop, and then you have a square root. You put the square root equals 0, you solve the equation, you get that number. No, there's nothing fancy. It's just a question of numerics in the one loop calculation. So numerical simulations. So numerical simulations, okay, we did simulations for NF equal 2 in the standard abelian Higgs model, compact abelian Higgs model. And we observed only Landau-Ginzburg-Wilson behavior. So for NF equal 2, we found O3 behavior exactly as predicted. For any larger value, we observed first order transition, even in the limit in which NF goes to infinity, which in a sense tells us that the textbook solution of the lattice CPN model is wrong. Is wrong, and I think that some of it was already in the paper by Alan and Starinets, in which he was making a lot of discussion about the assumptions. Because there are lots of assumptions here when you do the solution in the large n limit. And of course, we now know that one of those assumptions fails. And this is why the textbook solution of the large N CPN model is wrong. Essentially, it predicts a second order phase transition, a very specific coupling, but instead, the reality is that there is only a first order transition. But here, anyway, everything looks like there is no field theory, fixed point, no charge fixed points, only the Landau-Ginzburg-Wilson one. So apparently, in the usual compact abelian Higgs model, there is no evidence of the presence of those fixed points which are predicted by the field theory. Then we started the non-compact abelian Higgs model. The non-compact Higgs model has more complex phase diagram, which contains a lot of different lines. I don't have much time to discuss the different lines, but there is one new line which plays a very important role, which is the so-called MH line, which is written there. The MH line is a line along which there is a topological transition. Topological transition means is a line where the gauge degrees of freedom have a transition, but of course, gauge degrees of freedom cannot have a local order parameter. So it's a transition without local order parameter. And this transition already occurs when this parameter J, which is the coupling, the scalar coupling, is infinite. And we know that it is an inverted XY model, and in the same universality class of the O2 standard spin transition. And that transition goes inside the phase diagram and plays a critical role in the sense that it divides the standard line where the matter fields have a transition, which is the CM and CH line, into two parts. Along the CM line, nothing happens. We observe exactly the same behavior as in the compact model. But along the CH line, we find this charge fixed points. So I'll show you very briefly. I don't want to discuss the MH line because I don't have time. But essentially, the CM line is this transition, we have everything exactly as in the compact model. Because the gauge coupling is small, we have all three continuous transitions when the number of flavor is 2, and first order transitions for any larger value NF. On the other hand, on the CH line, for 2 and 4, so when the number of flavor is small, the transition is first order, but then the transition becomes continuous for larger values of the number of flavor, and we verified it was continuous for 10, 15, and 25. So this transition is not predicted by the Landau-Ginzburg-Wilson framework, because in that framework, all transitions with a larger number of flavors, larger than 2, should always be first order. So the natural hypothesis that you can make is that this transition is associated with the charge fixed points which are predicted by field theory. And so we did some checks. And of course, the checks that you can do, and they're not very much, but we have 1/n expansion. And since we are doing simulations for quite large number of values of flavor, so 25, 15, 10, we compare the estimates of the exponents with the large N estimates which are obtained in the field theory framework. And then you can see, essentially for 25, there is perfect agreement, well, essentially perfect agreement between the numerical estimates, which are nu and eta q, and the estimates large N, which are eta sub ln and nu sub ln. As you can see, those two numbers are essentially in very good agreement, which is our best proof, the only proof I must say, that that transition is indeed the transition which is predicted by field theory. So we have now evidence that field theory predicts correctly some transitions in the abelian Higgs model. But first, these transitions are not visible in the compact model. And this is probably related to the fact that the compact models has the monopole problem, while this monopole problem is absent in the non-compact version. Although it's not completely true, because what I'm saying, because now we have also another system in which the Hamiltonian is compact, but still we observe the charge fixed points. So the model which we have is a model in which the field has charge Q with Q larger than 1. So the standard abelian Higgs model is a model in which the field, the scalar field, has charge 1. If you introduce the charge, higher values of the charge, so higher representations of the U1 symmetry. So you introduce the charge 2 means that the second representation, the second U1 representation for the charge field, then you observe the charge fixed points even in the compact model. And in the compact model, there are monopoles, but of course, if you change the charge, part of them, of course, are removed. So this means that you need to remove the monopoles, but not all of them, to observe the charge fixed points, which is a funny thing. We did some other checks with a student, which is here, who's beginning the PhD here in SISSA this year. We did some simulations with ZQ gauge symmetry, so a finite gauge symmetry, and nothing happens. Unfortunately, nothing happens. There's no charge fixed points. But Claudio Bonatti, with other students in Pisa, has done simulations with a different version in which the continuous R group of gauge symmetry is replaced by a discrete but infinite, and so it's something like Z group. And in this case, the charge fixed points occurs again. So the charge fixed points is a little bit stable with respect to changes of the gauge symmetry. So in the non-compact model, of course, the gauge group is the real numbers, is the group of real numbers, the additive group of real numbers. If you replace the additive group of real numbers with something which is more or less Z, so the number of integers, then in this case, the charge fixed point still remains there, does not disappear. But if you just replace that with a discrete finite group, it's killed. So it says that there is some stability in the presence of the charge fixed point. So you can change the gauge group, still maintain the charge fixed points, but of course you have to be careful. You have to be careful. You should not take out too much. So conclusions, we studied several different models. The motivation, as I said, was that of understanding these models which come out from this emergent symmetry, gauge symmetry scenario. And for two flavors, there is no problem. The Landau-Ginzburg-Wilson approach works perfectly. We observe the O3 behavior in any model. You can do any type of changes as long as the gauge invariant of the parameter is the same. You always observe the O3 transition. There is really no problem. Then we investigated the charge fixed point, and we observed that the charge fixed point exists for n larger than some number between 5 and 9. We don't know exactly where it is, but certainly much smaller than 183, which tells you that, of course, the epsilon expansion is interesting, but not quantitatively predictive, because you get something, you expect something more than 100, and then effectively in 3 dimensions is a number of order 10. So it's a huge difference which cannot be predicted by the expansion. And we did also some work in the non-abelian case. And I must say that while the non-charge fixed point, the Landau-Ginzburg-Wilson fixed points are easy to find, whenever you expect them, they are there. The charge fixed points are a bit elusive. So in present, we only have one evidence, not very strong, of the existence of this charge fixed point. It is in this SUN model, when the number of flavors is 40. So a big number, of course, of no relevance whatsoever for experiments. But if you have a system with 40 flavors, you see something which is continuous transition, apparently, which cannot be described by the Landau-Ginzburg-Wilson approach. And we think, but we have no proof, that it may be related to some kind of charge fixed point which appears in the gauge theory, in the related gauge theory with SUN fields. Well, this is essentially all. Now, perspectives. Well, perspective, this is something we are doing now, not understanding much, I must say. What to do with fermions? Of course, up to now, we have discussed the behavior of scalars coupled to gauge theories, to gauge fields. And the interesting thing would be to couple fermions to gauge fields and understand the behavior. And we are presently working on the Gross-Never model And okay, it's quite difficult. It's very difficult to understand exactly what's happening here. But I think that we really need to better understand the behavior of the systems with fermions, because they are really everywhere. I mean, if you want to have something which can be compared with experiments, most of the models involve fermions. And so we really need to have some kind of understanding of the critical behavior of the universality classes that these models show. And at present, there are some work, mainly in the quantum community. So people are really doing quantum simulations on quantum systems. But a general renormalization group framework, as we have for systems with global symmetries, I think is completely lacking. So we really need to understand better what's going on there. Okay, thank you very much.
Thank you very much. Questions?
So we have seen that there are variants of the original system that you have studied for which this kind of transition still exists. And there is any hope of finding one variation of the model for which the epsilon expansion is less wide and a bit more reasonable at epsilon equal 1, or all these variants are epsilon expansion that becomes even more bad?
Yeah, right. Okay, apparently the abelian case is the best one. Because if you do the same in SUN, I don't remember the numbers, but I mean, in 4 dimensions, the limiting value is some kind of 400 and something. I'm not sure the 400, but it's a bigger number than that. So in the epsilon expansion approach in 4 dimensions, apparently these charge fixed points occur only when the number of components is tremendously large. And in principle, you say, well, they're really, you cannot really see them in 3 dimensions. But of course, the result that we have in the abelian case, in which we started from 183, and the fact that we see the transition at 10, tells you that probably those numbers have no relevance whatsoever. And indeed, in the SUN, we have this transition with 40 flavors, which is already a big number. I mean, 40 is not small, but still is not 400 and something, which is predicted by the epsilon expansion. So the epsilon expansion predicts the existence for very large, when the number of components is large, of these charge fixed points, but from a quantitative point of view, it's completely irrelevant. I mean, it doesn't tell you anything about it. So you really have no idea where the critical value is in 3 dimensions. You really have to do the simulations and hope. Because if it were 60, we wouldn't find it, because we decided 40 is the largest number that we can simulate, and it was 45, we wouldn't see it.
Why this happened?
Not that I know. Not that I know. I mean, the only thing that you observe is that the corrections are huge. So this tells you that those numbers will be corrected. But of course, this is a non-Borel summable expansion, not even Borel summable. I mean, it's.
So. 183, 1 minus
1.7
okay.
epsilon. So it's already bigger than 1. So if you just put epsilon equal to 1, the first correction gives you a negative number.
So that is telling you that.
Yes, it tells you that it's unreliable, and it's also non-Borel summable. This is the problem when you have gauge fields. Yeah, 1/n expansion looks good. Yes.
As long as they stay in the order of magnitude of what exponents bigger than a half, then that's the end where you like.
Well, the 1/n, however, is very smooth. In principle, it could predict even something at NF equal 3, reasonably, because it's 1 with a tiny correction. So the 1/n is really the expansion that we use to compare with the data, because it's the only one that effectively we have and seems to be predicted. But it doesn't tell you anything about the critical value. because 25 is good, but also 10 would be good, also 4 would be good. It's still reasonable. It's still reasonable. Then maybe it's not the correct value, but it's still reasonable. And then, of course, at 4, you expect other terms to come in. Hmm?
5.
Not 2. No, yes, not 2, but if you take two terms, you get something very reasonable.
Maybe another question.
It's a commentary from somebody very rusted in field theory, but say that you had a similar phenomenon in the Potts model, and you realize that something happens for the number of colors that is above 40. And so you don't want to make a huge simulation for a model with 50 colors. Well, the Potts model has a Fortuny-Castellan representation in which Q is just a parameter.
Mm-hmm.
There is maybe a representation for these models in which n is a parameter and you can put it 40 without...
Not that I know. I mean, I don't know how to do gauge theories with non-integer values of n. I don't know. It would be nice to have it, of course, but I don't think we have it. Imagine, this is a U1 variable, and then the spins are complex vectors. It's not that easy to, I mean, everything works in the Potts model because you have just 2 possibilities for the energy. And of course, you can probably generalize to systems in which you have a finite number of possibilities. But here, I mean, it's a continuous system.
ON model also is a continuum symmetry. And it also has a formulation which is purely...
Yes, in principle. Well, you know. Yes, 1 plus kappa sigma. Yeah, the one that is used for n less than 2. Yes, but it does not. I mean, it's not good for n larger than 2. No. That representation works. Yeah.
Okay. If there are no other questions, let's thank Andrea again.